resonance theory. So what is resonance theory? Remember, we apply resonance theory for cases in which so there are molecules, and this is the example that's on the lecture, but I'll give you another one here, for example. In a molecule like this, and versus, let's say, a molecule like this, all right? So, in a molecule like this one, we have basically two isolated bubbles. Remember, one of the things that we learned in resonance is there are some molecules for which a single Lewis structure does not give you the accurate representation of the real structure of that atom, of that molecular ion. Okay, that we need to understand. So, in those cases, we need to use a different tool, in this case, resonance theory, which basically what we're going to do is, instead of using just one, right, we're going to use several resonance structures, which basically several Lewis structures, and we're going to basically put these structures in brackets and relay them by means of this double-headed arrow, right? So we can have here structure A, just to give you an example, and then we'll have structure B, and then so we are using the brackets because we want to tell people that we are actually working with resonance theories, right? So structure A, and we can say, let's say there's another structure here, structure B, and then structure C. So what we're indicating, so this is the first thing that you need to understand, is that what we are indicating here is that the real structure of this molecule of iron is a hybrid of structures A, B, and C. None of these structures, A, B, or C, they do not exist. Remember, when you have an equilibrium double arrow in general chemistry, there is an equilibrium between structure A and structure B because they both coexist in solution. In resonance theory, we are using the brackets, we are using the double-headed arrows to show people that this A, B, and C are simply three different Lewis structures that they don't exist. The real molecule, so the real molecule, I'm going to write it over here, is a hybrid of A, B, and C. Okay, that's the number one thing that we need to understand. So when we have cases in which a single Lewis structure is not enough, it's not good enough, we need to go to resonance theory, and we need to then use this symbolism to show people exactly what is the structure of this molecular ion. So, now, the next question is, how do you know when do you have to apply resonance theory to give the real representation of a molecular ion? Okay, so when to use resonance? That's a big question. And the answer to that question is whenever whenever there is three or more p orbitals next to one another and properly aligned. Okay? And basically what this means is to have three or more sp2, three or more p orbitals, or we can say here sp2 atoms next to one another and properly aligned. So whenever you see a system with three or more sp2 atoms next to one another and properly aligned, you can tell that that is delocalized. And because it's delocalized, a single Lewis structure will not be enough to show the real structure of this molecular ion. Therefore, we need to use in those cases resonance theory to explain the real structure of the molecule. So I gave you two examples here. So if we assign hybridization on the structure on the right, sp2 hybridizes this carbon, sp2 hybridizes this carbon. The next one is sp3. Okay. On this side of the molecule, we have a double bond here. On the right side of the double bond, sp3. On the left side, sp3. So, is this structure a delocalized system? No, because there is a maximum of 2, and these 2 are atoms with the same electronegativity. Remember, I gave you some material to read. Whenever you have, let's say, the carbon functional group, right? If you have a double bond in which you have atoms with different electronegativity, in this case, to show the bond polarity using the resonance theory, you can indeed say something like, okay, so let me finish drawing those structures here. So 2 bond pairs, and then in a case like this, when you have a double bond with 2 atoms with different electronegativity, you can actually say, okay, so there is a certain degree of delocalization. It's not delocalization, so basically this bond is polarized, right? So you can show the resonance theory of the coordinate functional group. And to show the resonance structures, remember we use the curve power symbolism. That's another thing that is very important to know in this chapter. So the curve power is going to show you the flow of pi electrons in resonance structures. Remember the sigma bonds, they all remain the same in both structures. So if I were to draw the resulting resonance structure of the curve power that I drew on the left side here, okay, if I were to show that, I can say that pi electrons are going toward the oxygen, therefore I need to add there in the resulting molecule an extra lone pair and a negative charge. And then in that case, because of that, then the carbon is left now with 3 bonds, therefore the carbon must be positively charged. So a couple of things about this that I want to use this example to explain how resonance works. Once again, in resonance structure, we only show the flow of pi electrons. Okay, that's the only thing we show. We don't move atoms, we don't move sigma bonds whatsoever. Just the flow of pi electrons. So the second thing is how to use curve arrows. This is in the lecture too. It's in the material I gave you to read. So curve arrows are only departing from electron sources. Okay, electron sources that you know, basically pi bonds and lone pairs. And they're ending, the arrow is ending wherever these electrons are going. So they could be ending either in an atom to form now a lone pair, as in this case, or they could be ending in a new bond, in a new pi bond next to the one that it was broken. Okay. So the second thing is once you flow the pi electron flow bond toward the oxygen, obviously the carbon is left with positive charge. The total charge of every single resonance structure is the same. Okay? Total charge here is 0. Total charge here is 0. Does this structure exist? No. Does this structure exist? No. The real combination is a hybrid of both of them. This is important because when you see in textbooks the carbonyl functional group, everybody is going to draw a carbonyl like this. Okay, so you'll see this is acetone. But everybody understands, every organic chemist understands that even though this is what you show on the paper, there is a slightly contribution of the structure to this real structure of this atom. So this hybrid of these two is basically indicating that this bond is polarized, that there is an excess of electrons over the oxygen and an electron deficiency over the carbon. This is exactly as we have been discussing before, according to electronegativity. Okay? So you need to basically be very familiar with identifying systems in which you have delocalization. And to continue with giving you another example, so we said before that electrons will be delocalized, or charge will be delocalized whenever you have two or more sp bonds next to one another. We know an sp2 atom might be an atom with a double bond. Another example of sp2 atoms are atoms that are, for example, let me give you here an example. So we have, okay, so let's see. So what's the name of this functional group that I have on the board? Mi. So that's an Mi functional group. So the first thing we need to do is to complete the Lewis structure. So if I were to complete the Lewis structure for this compound, I will need to add basically a lone pair on the nitrogen and two lone pairs on the oxygen, right? So if we want to understand if this system is a delocalized system or not, we first need to assign hybridization to every single atom. Every atom, not only carbon, nitrogen, oxygens, halogens, any atom, right? So hybridization here is sp2, obviously there is a double bond. Hybridization here is sp2 because of the same reason. What is the hybridization of the nitrogen atom from the Mi group? So the nitrogen in the Mi group is sp2 hybridized. The reason for that is because the nitrogen has a lone pair, and whenever you have an atom with lone pairs next to a double bond, or next to a charge, a positive charge, right? This atom will be sp2 hybridized. So we have one sp2, two sp2, three sp2 atoms. Therefore, this is indeed a localized system, and we need to use resonance to show the contribution of electrons. So basically, remember another thing that I want to point, you're doing the curve arrows, right? So it's important to understand how the electrons flow. In this case, the lone pair is forming a double bond here in the next atom. And then if you put a double bond over here, you need to break a bond in the carbonyl because you don't want a carbon with 5 bonds, obviously, right? So I'm going to draw the next resonance structure, which is pretty simple. And then here indicating by the arrow that this bond now is broken. So we have an oxygen there. So we need to add there basically a lone pair and the charge. And then obviously if the lone pair is on the nitrogen is going to form a double bond, now we need to place a double bond here. And if the double bond is there, obviously that nitrogen will be positively charged. So remember, formal charges are very important when you're doing resonance structures. So the total charge of every resonance structure must be the same. Total charge of the structure on the left is 0. Total charge of the structure of the right is also 0. Okay, so this is an example. Once again, if you have atoms with double bonds, they will be sp2 hybridized. Second example would be an atom with lone pairs next to a double bond. That atom will be also sp2 hybridized. And the last example that I can give you, let's say let's look at this ion here, okay? And then my question would be, if this is a delocalized system, to answer this question, we need to assign hybridization. First of all, we need to complete Lewis structures. So to complete the Lewis structure, I to add 2 lone pairs on the oxygen, so I'm going to do this right now. 1, 2 lone pairs. That's my new structure. Next, I need to assign hybridization to every carbon atom. So what is the hybridization of this carbon here? sp3, no multiple bonds, so 4 single bonds on that carbon, so that's sp3 hybridized, right? The next carbon, sp2 hybridized, it has a double bond, so that's pretty simple to assign hybridization to. The next to it is also p2, once again, another double bond. And then what is the name of this ion, by the way? A carbon with a positive charge, how do we call that? It's a carbocation. So the carbon with a is a carbocation, okay? So carbon with a positive charge is a carbocation, don't forget that. And what is the hybridization of the carbon that actually bears the positive charge? What is the hybridization? It's an sp2 hybridized carbon. Remember, a carbon like that, and that is in the picture that I gave, the reading that I gave you, right? A carbocation is a carbon that is trigonal planar. The bond angle is 120, right? And it does have an empty p orbital. So this is the structure of a carbocation, okay? The carbocation is a carbon with 3 single sigma bonds, 1, 2, 3 sigma bonds, and an empty p orbital perpendicular to the plane of the molecule. So it's sp2 hybridized. The angle in between the sigma bond is 120. So trigonal planar is a geometry. The carbocation is flat, and there is a p orbital perpendicular to the plane of the molecule in that space. Okay. So hybridization here is sp2, and then what is the hybridization of the oxygen atom in this molecule? What do you guys think? So it's an sp2 hybridized atom because we have an atom with lone pairs next to a charge, a carbocation. So once again, lone pairs next to a double bond, that's sp2. Lone pairs next to a carbocation, that is sp2 as well. Okay. So according to this picture, we have 1, 2, 3, and 4 sp2 hybrid atoms. So is this a delocalized system? It is. So a single structure doesn't really show the structure, the real structure of this ion. So we need to use resonance theory to show the different structures. Right? So I'm gonna show a curved arrow departing from the double bond. Curved arrows are always departing from electron sources. In this case, a pi bond, and ending in a pi bond, now a new pi bond that is going to be formed. So basically the pi bond is moving from the left to the right. So I'm going to fix that. This is indicated, and if that is the case, now the positive charge is going to be over here because this carbon is going to be left with 3 bonds. So the positive charge is going to be over here. So that's a resonance structure. Is there another resonance structure that I need to draw for this molecule, for this ion? Yes, because we can see how. So this resonance structure accounts for the delocalizations toward this side of the molecule. But next, so to the right side, I do have also an sp2 atom. So I need to show that. Okay. So once again, the curved arrow is departing from electron sources and is ending, in this case, on a new pi bond that is going to be formed. Okay. The total charge of every resonance structure is the same. So if this is happening, I need to then delete a lone pair, because obviously that lone pair is being used for a new pi bond, okay? And if that happens, now I'm left with an oxygen with 3 bonds, and that oxygen must be then positively charged, okay? And these will be my resonance structures. So the real hybrid, so the real structure is a hybrid of these 3 structures. This is so important, guys, for you to see. So basically, that if the way I drew the molecule initially, and I want to repeat this idea, one of the most important things about resonance, if you look at this molecule, at this ion, just like that, you only see the positive charge on this carbon, okay? But this is a delocalized system, which basically means that the positive charge, the electron deficiency, is shared in between this carbon and this carbon over here, because the system is delocalized, because this structure does not exist. The real structure is a hybrid of these 3, and in this hybrid, the positive charge is shared in between this carbon here and this carbon over here, and also obviously over the oxygen. Okay, so that's a really important thing to keep in mind. The positive charge is not fully localized over a single carbon. Because it's a delocalized system, the positive charge is delocalized, is shared in between this carbon here, and the oxygen atom. That's a real structure, a hybrid of these 3 structures. We will learn in organic chemistry in the next semester that not all the resonance structures will have the same contribution to the hybrid. Some will contribute more than others. But this is something that I want to stop. I don't want you guys to be an expert right now. Just want you to know the basics about resonance. Okay? So this is pretty much it. What you need to know about resonance, once again, read the reading material that I gave you, understand what is the resonance theory, and practice problems that I gave you for inorganic and organic molecules, okay? How to use the curved arrow symbolism to create resonance structures, and understanding that the real thing is a hybrid of the 3 of them. So you need to be able to molecule and assign hybridization to every single carbon atom or oxygen or nitrogen, any single atom in that molecular ion. Once you assign hybridization correctly, then you can determine whether or not you need to use resonance structure in this example. And if you do, then you need to use the curved arrow symbolism to show the structure of the hybrid.